All right, let's do a question today. I'm gonna do an easy one today. It's still early in the morning for me. Easy is probably all I can do right now. Not all the easy ones that we code are actually easy. They're not graded very consistently. Some of them may have like 2 lines of code, but the algorithm takes forever to come up with, or vice versa. Oh, that's a lot of downloads. Oh, this looks okay. Happy number. A happy number is a number defined by the following process. Starting with any positive integer, replace the number by the sum of the squares of its digits and repeat the process until the number equals 1, where it will stay. Interesting, okay. Or loops endlessly in a cycle, which does not include 1. Those numbers for which this process ends in 1 are happy numbers, okay. Interesting. What is the actual question though? Is happy. So given a number, return a boolean. So the alternative is it loops. This seems more mathy of a question, but let's take a look. So it would end if the number ends up being essentially like 100 or something, 1,000. Because you can't have zeros in front of the ones. You can only have zeros after the 1. So you would need digits where the squares sum up to 100, and 6 and 8 is one of those. So what I'm thinking now is one way to approach this is to figure out some heuristic to understand when numbers do match a pattern, when they consist of numbers that eventually add up to some magical 100 or 1000. The other approach is probably just do this for a number. Take the number apart, square them, get a new number, do the same thing, and see if it repeats. But the thing is, you wouldn't know if it repeats. If it just goes on for a long time, like, is that, like, how do you know when to end this process? For example, if 19 became another number, and it became another number, and it just kept on going to become different numbers, does the number get smaller? So for any number with, let's say, 2 digits, the max you can have is 99. And so the max you can have for the squares is 9 squared plus 9 squared. And if you have 3 digits, the max you can have is 3 times 9 squared. Which is like under 300. So the sum of this number, so when you run this process on this number, it would only be able to get as big as what is proportional to the length of this, times about 100. So if it's a two-digit number, the max you can get is maybe like 100 to 200. If it's 3 digits, it's like 300. If it's 4 digits, it's like 400. Which is good, because if we were keeping track of, is this thing going to be infinite, we can just store these numbers, and there's not too many of them. For like a 6-digit number, we only have to try a max of like 600 times. and that seems actually okay. Okay, so I think what I'm going to do is just do this process, keep track of these numbers in like a map, so that I can access this later quickly. I only want to know if we've previously seen it. So if we've seen it, then we know it repeats. But if it eventually becomes 1, then we know this is a happy number. Okay. So 19, 8. Is happy is the function. We want to take apart the number, so we want to convert it to string. And then we want to compare, split it into digits. So that gives us each digit as a separate string in a list. And then we want to convert it back to numbers. I think it's parse ints or something. Oh, it totally does look different. And the radix is by default. Usually defaulting. Okay, yeah. I think if you ever have something like 0 something, and it'll parse that as a octal base of 8. Okay, we've got our digits. We want to sum them. And if the sum is 1, return true. And so we want to do this in a while loop. Else if previously seen, if it's in there, that means we've looped through, if we're infinite looping, we're just going to keep on repeating this number. Return false. Otherwise, previously seen is true. And yeah, so what worries me a little bit is that I wrote an infinite loop here, and it's not absolutely clear that it's going to exit. Or at least it's not very explicit that it's going to exit. But let's run it and see what happens. It's not happy about this for some reason. I'm not sure what part of ES6 this supports. So let's separate this out first. Okay, that looks right. All right, it just seems like I can't do this then. and I can never remember the call semantics or the call arguments for this. All right, send that. Is math.sum not a thing? How let's add. I'm confusing Python with this, so maybe I'll do reduce, which I also can't remember either. Reduce is a helpful function sometimes, but I can't remember how to use it properly. Get a callback. You start with a thing. You start with 0 because we want a sum. Actually, you don't need it. Digit square. Do you need two things? Yeah. And I'm not sure if I'm doing this right, so I'm going to console log it. 82. Okay, that looks right. But it is a happy number, so because I keep on doing the same thing. Let's make this more explicit so I don't end up using incorrect values like I did last time. I want num to be the new thing, which is digits. It's the sum. So it had 82, 68, 101. Okay, that seemed like it worked. I'm actually not too sure how to go about testing this because I don't know any case that infinite loops. So I'm just going to submit it into LeetCode and see what happens. Okay, but that wasn't very satisfying. I felt like I wanted to know what numbers were not happy numbers there. But that's pretty straightforward. The time complexity of the function is, well, it's hard to tell because it depends on input, but for every iteration we do, it's proportional. So O of n being the number of digits in the input as expected. And the space we've used up here, we keep a map. The space the map takes up is proportional to the number of rounds we do, which like we'd have to do here. We allocate some strings and arrays here. So when I did this with a split, it actually allocated an array, a new array, with every number in it. And then it immediately mapped it to numbers, so that array was just thrown away. Garbage collected, so we'll just assume that it doesn't take up space over the time of execution. So the moment it's been converted to a map, the first array is gone, or the moment it's been converted to integers. And likewise for the digits, the moment we squared them, we didn't need that anymore. Yeah, so we do some allocations in the middle here, but we don't keep them around and they go away. So that's a pretty straightforward solution. I think the leap for this question came from, how long did that take? About 10 minutes end to end. I think the leap from this came from knowing that how many rounds you do is pretty small. Like no matter how big this number gets, the input number gets, the number of rounds you do is only proportional to the number of digits. So it will never execute for like a billion times if your number was 1 billion. It was only going to be a couple hundred or at most a couple thousand. I think without that knowledge, I would be hesitant to go down this path of this algorithm, because it would possibly execute for a long time. And I think that's usually like a sign. Like if you don't know how long it's gonna take, as in if you know if you don't know that it's gonna take a short amount of time, then something is possibly wonky with it. I'm still trying to think if there is a way to determine if the numbers somehow like square up to 100 or 1,000, but I don't know enough math to figure out if perfect squares or whatever they sum up to some magical number. I think that's some formula, or that's some theorem. So that's that quick, easy, short video. I'll probably do a hard one next time, and that'll be more involved. So that's fun.